Alright everyone, so today we're going to discuss about how we can form some solutions, and when we react to solutions, what occurs. Is there a reaction that takes place? And then maybe we'll talk a little bit about table G if we have time. So we can form solutions either chemically or physically. And here's an example of, a physical situation where we take some sodium chloride and we add it to water, and then we form a solution of sodium chloride, aqueous solution. And what's happening in this case is the sodium ions and the chloride ions are breaking apart. They're interacting with the water, but this is a physical change. And I know this is a physical change because very quickly I could get this back if I just evaporate out the water. I could be left with the NaCl solid, which is what I started with. And so we can see that this was a physical change. And we made the solution through physical means. Now, what happens if I take two substances and mix them together? Like here I have my magnesium, I'm adding it to hydrochloric acid, which is a solution in itself. And I want to create a new solution, magnesium chloride. Well, I do this through a chemical means. There is a gas produced that escapes. Even if I evaporate all the water at this point, I will get back MgCl2. I won't get back the hydrochloric acid or the magnesium metal. So in both cases we formed solutions. In the first case there wasn't a chemical change, but in the second case there was, and we formed a new solution that has a new substance in it. So what I wanted to discuss with you now is writing reactions between two ionic substances. And we're going to do this through a process where we have two solutions. Both of these are aqueous. And you can always check table F and see that they're soluble, but in this case, we won't be soluble actually, because these are mixed up. So let me actually start over here as I look at this. We'd have something like KNO3. No, that's wrong. Sorry. We'd have Ki plus PbNO3 too. These are both aqueous. Now both of these solutions exist as ions, and we'll deal with that in a little bit. But let's see what would happen if we combine them together. We mix them, the two solutions, in separate beakers, and we get a result. Now let's look at what the result would be, the products that form. Well, first I want to assign charges to the elements that I'm starting with, the K plus and the I minus, the Pb plus 2 and the NO3 minus, and these you should know pretty well. So now I'm going to recombine them. The positive ions, the Pb, is going to go with the negative ion I, and the K positive and the NO3 are going to combine together. And the way that they combine together, they'll combine in such a way where the positive and negative ions will try and cancel each other out, and so you'll have to write new formulas. K plus NO3 minus plus PbI2. And so now when I look at these two, I make sure that the charges balance. So K was positive, NO3 was negative, Pb was positive 2, I was negative 1. So they cancel out and they balance like this. Notice that the equation overall isn't balanced though. We have a different number of I's and a different number of KNO3's. And so to balance this I would need 2 of these Ki's, and I would need 2 of these KNO3's, and now we have a balanced equation. Now this is called my molecular equation because it shows things as molecules, but these are all ionic compounds and they don't exist as molecules. So how can I go about getting these to actually represent what's really happening? And that's where the idea of a net ionic comes in. Before I do that though, I want to check my products, and so I look at my first product and I go to table F and I see that K is a group 1 metal, it's always soluble, this is going to be aqueous. And I look at PbI2 and I see I minus is a halide, and when it's combined with Pb it actually is insoluble, and so this is a solid. So now I say to myself, how can I show this solid forming? How can I get a good representation of what's going on and an idea of, okay, yeah, the solid is forming and there's ions that are reacting? And that's where the net ionic comes into play. So the Ki, it is aqueous and it is ionic. And what that means is that it will actually break up into the ions that make it up. We'll have 2 K positives and 2 I minuses, The Pb will also do the same thing, the Pb plus 2 and the 2NO3. Now notice what I did here. The 2 little subscript became the coefficient. That's important to note. Notice it's not NO with a 3 in front. NO3 is a polyatomic ion, but there are 2 of them. This results in another aqueous salt, K+, there's 2 of them, and 2NO3 minus, and then PbI2. PbI2 is a solid, and since it's a solid, those ions are stuck together. They're not broken apart, and so I keep them together. Now, this is called my total ionic. It shows all of the ions. But the thing is this, is that there are ions in here on both sides that aren't doing anything. And we can see that here, if we were to highlight them, we have our K and our K, our NO3 and our NO3, and they're exactly the same. And this is just like a math equation where you'd have like 2x on the left and 2x on the right. You can cross out those like terms. And we're going to do the same thing here. We're going to cross out the 2 Ks and the 2 NO3s. They are going to cancel. And we are going to be left with 2I minus plus Pb plus 2 yields PbI2. And this last equation here, which I'll put a little squiggly line around, is what we're looking for. This is our net ionic equation. This is what, in real chemistry, when you do more advanced chemistry, this is what people look for. The molecular equation, unless I put in the phases down here, doesn't really tell me that there's a reaction occurring in what solid forms. The total ionic is cumbersome because it has, like, all of this extra stuff in it, and those things are unnecessary. But then the net ionic, it's really, really compacted down to what's important and what's reacting. So this is the idea behind what we're going to do in the lab tomorrow. We're going to actually react together substances, and we're going to get our net ionic equations, and we're going to see the precipitates that form. So one thing I just want to touch upon, I'm not going to have time to do all of table G, but I want to talk to you about what is meant by solubility. And this is a topic on solutions, and solubility is really describing how much solute can be dissolved in a given amount of solvent at a particular temperature. Pretty much the only thing that can change solubility is temperature. Temperature is the only thing that can change how much total solute dissolves in a solvent. The exception to that is if you have a gas. And when you have a gas, then you can actually pressurize it and dissolve more that way. Now, depending on what you're dissolving, sometimes a higher temperature will allow you to dissolve more. Sometimes a higher temperature will actually allow you to dissolve less. And we'll talk about those specifics. So, saturated, when we talk about a saturated solution, this is describing a solution in which you have the maximum amount of solute dissolved in a given amount of solvent at that specific temperature. You can't fit any more. If we're unsaturated, that actually means that you haven't put in the full amount of solute. You have less than the maximum at that temperature. And then we have this weird situation, supersaturated. Supersaturated solutions don't happen naturally. You can't just look at the solution and get more to dissolve at a specific temperature. You have to trick the solution. And you do that by making it at a higher temperature where generally you can dissolve more of the solute and then slowly cooling it down. If you slowly cool it down, all that extra solute that shouldn't dissolve actually stays suspended in the solution. But it is one of the coolest things to see because it's very unstable. And a lot of times, if you disturb that supersaturated solution, all that extra solute will come crashing out. Now I'll show you a demo to really illustrate that, and if I can't get the demo to work because it's very finicky, I will instead show you a video, but either way. So we're going to look at a graph that relates these things. It's table G. And what we're going to see is that on table G, temperature is the major factor. We're going to look at different solids and see how their solubility increases when the temperature increases. And we're going to look at a few gases that are on that chart and how their solubility decreases. And again, this ties back to oxygen dissolving in water, how fish need this oxygen, and how in fact when the temperature is raised of a body of water due to thermal pollution, that the fish cannot survive as well as they could at the cooler temperature. Again, pressure can affect solubility. If it's a gas, you can increase the pressure and get the gas to dissolve. So here's a visual of a few of these things. So here's coffee and the idea of dissolving sugar. And if any of you have ever experienced this, you have hot coffee or hot tea and you can put sugar in it, it dissolves readily. You try and do this in iced coffee, good luck. Gases with pressure, having pressurized soda bottles and cans, they are bottled and canned under high pressure. And when we open up those cans and bottles, you can hear that fizzing and you can see those bubbles starting to form coming out of solution. And then again, having oxygen for fish to breathe and changing the temperature of the water. Now, what I said, and we'll do this next time, solubility curves, we're going to look at the solubility curves, table G, and use the numbers on there to interpret solubility, saturation, unsaturation, and supersaturation. All right, thanks for watching.